you see now?
So, yes, now it's okay. So let us check about the delay.
I think the delay should be fine.
That I think. I remember. Can you check that whether you're taking the voice from the headset or the camera?
I think I'm taking it from the headset because I have done that setting already. It works fine.
You can hear the background noise a little. Because of that, I asked that.
It's just too sensitive.
Oh, okay.
That's the reason. Everything is fine?
So less than 5 seconds of.
Okay, that's good.
Okay, you can stop.
Okay, so hello everyone, and I'm very sorry that we have faced this technical difficulty. This is the first time I'm taking a lecture like that, and I already configured it in the morning, but everything was fine, but it wasn't working now. And that's the usual business, I think. When you want something to work, it never works, especially in meetings and stuff like that. And I see there are a lot of comments from the online participants. So for people online who seeing me, don't be surprised. So today's lecture will be conducted by me because Aki is feeling under the weather, and for that reason he was unable to come to the office today. But anything, I think we have wasted a lot of time already, so we will get started. So as you can see the screen, can you? No.
So, should I stay or should I go and come back?
You can stay if you like.
Oh, it's okay.
There's HDMI 2, I think, right? Yeah, HDMI 1. Mostaba, can you take care of this? Can you put the HDMI 1 on? So I'm using HDMI 1, or should I use HDMI 2?
No, since there's only HDMI 2 here.
Okay, then I'll use HDMI 2. Okay, you can see, guys?
Yes.
Okay, perfect. Okay, so far I think you guys have done. So welcome to the sixth lecture of the course entitled Simulation of a Mechatronic Machine. As Aki might have told you in the previous lecture that you have been reaching to the peak of the most difficult things, and very sorry to inform you he was lying to you, because today's lecture will be another peak at the same level, because it involves a lot of mathematical complex equations. And but don't worry, be with me, and we will try to make this journey enjoyable for you. Okay, so in today's lecture we will be mainly focusing on equations of motion, and that too there are many different equations of motion, many different methods available. We will be dealing with augmented formulation method. Okay, but before that, some sneak peek from last week's lecture. So in last week lectures, we learned that there are two kind of forces whenever we are dealing with physical systems, right? So there are this external forces, and then there are some inertial forces. We learned that we can express the external forces in terms of generalized coordinates. Is that word familiar to you guys? Okay. So using external forces, you can express any kind of forces acting on the body, which can be from hydraulic actuators, which can be from pneumatic systems, from spring dampers, from anything, right? Can you see my face now, online participants? There was a comment. I think yes now. Okay. So in a similar fashion, we can also use this inertial forces, and we can express that in terms of generalized coordinate. Now, what is the difference between generalized coordinate and global coordinate? Can someone answer me that? Anyone? Okay, so far, if you have been learning the tutorial as well, global coordinates are the coordinates that we know. For example, if we talk about 2D case, the x-axis, the y-axis, correct? These are our global coordinates. But the moment we say generalized coordinates can be anything that helps to express the entire uh, orientation and the translational motion of the body. In our case, in this tutorial, we have been using generalized coordinate as the x position of the body, the y position of the body, and the orientation of the body, correct? So our generalized coordinate has three components, our global coordinate has two components. So the way we have been dealing with external forces, is it is it better now, the voice for the online participants? Okay, perfect. Okay, so the way we have been dealing with this external forces, in the similar way we are going to deal with this internal forces. Now we learned that internal forces can be expressed as I don't know if I can type here. I'll try. Okay, so we know that we can express external forces as mass into the acceleration of the body, correct? And this acceleration is expressed in the global coordinate. Perfect. Okay, but we learned that this mass can be expressed as, so whenever we talk about this expression, we are talking about a particular point in space, a particle in space, right? And we have to incorporate the entire set of particles that is forming the body, correct? So for that we learned that we can express the mass of the body as density into the volume, and then this volume can be integrated over this entire volume of the body, and accordingly you can get the inertial force of the body. Now this inertial force needs to be mapped onto this generalized coordinates, because this inertial force is expressed in terms of global coordinates. How global coordinates? Because it's expressed in terms of the acceleration, and the acceleration, you see, it's, you by default, you know, there's the x component of the acceleration and the y component of this acceleration, correct? Okay, now moving on. So how we can express this inertial forces into generalized coordinates by using mapping. So for example, this is that mapping function, and how it comes? It comes because we use the concept of virtual work, and more specifically we use the concept of virtual displacement. So if you consider this inertial forces here, and you multiply that with infinitesimally small position, why this delta? It's meaning that it's extremely small. Don't go for the physical interpretation of this. Just mathematically in your mind imagine that there's a very small movement of this particular body, and this particular movement is, this particular displacement is called virtual displacement, and the work that is associated to this virtual displacement is called virtual work, correct? And for that reason we expressing virtual work as small delta and w. Okay, now we have learned earlier this mapping between the general the global coordinates can be done to the generalized coordinates using this mapping, where this mapping is saying that the partial derivative of your position with respect to the partial derivative of all the generalized coordinates. So moving on, basically we have also learned that the acceleration. Okay, I'm making some really bad drawings, guys, because I don't have that pointer like Aki, and even my laptop is not interactive that he could draw on his screen. So I'm trying my mouse to model it, so bear it with me. But anyways, so this acceleration of any point A can be expressed as a standard form, right? We have learned this already, guys. So we are just representing something. We know that a position can be expressed as the position of the center of the body coordinate system plus the rotation associated with it and u bar. This is the the expression for the position. When you double differentiate it with time, you can get the expression for the acceleration. And this acceleration can be expressed in a sophisticated form as shown here. Okay. Now, when we replace this acceleration term over here and also this partial derivative of the displacement term over here, which can be expressed as in a sophisticated form as this from the earlier lecture. So when we just use these two expressions within the expression for the inertial force, then we can see that the inertial force can be expressed in terms of generalized coordinates, right? So this is kind of the form which you can derive before the mathematical explanation. Now don't worry about the detailed maths involved. Try to understand the logic. We are coming from a global coordinate system which has two coordinates in a planar case. And we are shifting to a generalized coordinate which has three coordinates, right? So now when we will express this inertial force, it should have how many coordinates? Two or three? Three coordinates, correct? So just follow that part. Okay, now when you see this monster equation, you can see that when you will multiply these terms here, there will be two terms associated to this inertial force. The first term is some complicated matrix multiplied with the acceleration of the generalized coordinate. Correct? This is your generalized coordinate, yes or no? Correct. And similarly, there is another term which is related to the velocity of the generalized coordinate, and this term is called velocity vector. And the first term is called mass matrix. So we can see the moment. So earlier we had an expression like this, which is mass of the body into the acceleration of the generalized coordinate, right? And the moment we changed this expression to be expressed in generalized coordinates, we see now we have a term which is mass matrix multiplied by the generalized coordinate itself minus a quadratic velocity vector, because this vector is dependent on the angular velocity of the generalized coordinate in a quadratic form. That's why quadratic velocity vector. Is this clear for you guys? I think Aki already covered this in the last class, right? So this is just a summary of it. And for online participants, please feel free to ask me questions. I'm trying to see all your comments as well. So moving on. So we also learned that this mass matrix will have three different components. The first component is straightforward an identity matrix, because your mass in the global x and the global y, when they are translated to the generalized coordinate, the first two generalized coordinates are still the global x and the global y, right? So for that reason, it will be an identity matrix here with the mass terms in it. Then there will be mass moment of inertia term. So basically, when you have a mass associated to it for any body, for example, when I talk about this pen, okay, and when I try to rotate it, you always feel there is some moment of inertia which is acting on my fingers because of the mass of the body, right? So this term is exactly incorporating that term. Now, talking about the third one, which is this particular matrix, which is kind of the cross coupling term between the translational and the rotational motion. So, for example, this term here is considering the translational motion of the body. Why? Because the first two generalized coordinate is rx and ry, right? But the third generalized coordinate is theta. So theta is taking care of this mass moment of inertia, but when you talk about the cross coupling term, this is considering the coupling between the translational and the rotation motion. What is the physical significance of it? It's not so clear, and to be honest, it is just uh, for understanding purpose, see this as a mathematical term that whenever there's a translational and the rotational part involved, there will be some cross coupling term with them, right? Any questions so far? And I'm so very sorry, I'm trying to cover up for the for the time that I was late, but any questions? If anything is unclear to you guys, please raise your hand and ask me questions. I will be very happy to answer that. We are here to have 100% success rate today. Remember, Aki is watching us through this YouTube live. I hope so. Okay, so with that, we already have the first in class quiz. I will try to log in. So, guys, can you already log into your Socrative and see this question live there? What about online participants? Perfect. So let's take some time to answer this first in class quiz. So the first in class quiz is asking mass matrix of a body is a diagonal matrix if under what condition? So as we have learned in the previous tutorials or in the previous lecture that usually the first term is an identity matrix, right? And then the second term is the term associated to the mass moment of inertia. Now, in what condition or in what situation these terms, the third term, that is the coupling between the translational and the rotational movement, the mass associated to it would be zero. That's what the question is. And it depends on where is the body coordinate system associated, right? So the body coordinate system can be anywhere from the center of mass to within the body but not at the center of mass to outside the body, and it should not depend on the shape of the body, right? So what do you guys think? What should be the correct option? some guys in the chat window uh, are guessing it to be option A. May or may not be. So has everyone done answering it? Usually, how many people? How many? 80. And so, should we wait for another few minutes? Have everyone in the class answered this quiz? What about online participants? So there's a comment that will Aki dance if we score 100%? I will. One thing I can assure that the moment we have 100%, I will take a picture. I will send it to Aki right away, and I will ask him to make a dance video and send it to us. I'm very sorry. I know that some people left because of the delay. It was completely my fault. We were facing technical difficulty. Someone is saying that he cannot log in. Can someone in the chat window help him to log in? So the LUT, I think the room name is still LUT, right, Mostaba? LUT. Yeah, close the app and open again. That might help. Okay, I see that we have 60 participants. 61. The number is increasing. So what are your estimate, guys? How much percent success rate we will have? 80? I'm expecting it to be very low. 70. I'm saying 40%. 40. 85, 86. 10%. Let's see. Let's see. So let's see what's the correct answer. Whoa. You guys are already an expert. 89%. And I did not even explain this part, I think. But very well done, guys. That 89%. So going back to the presentation, explaining that again. So a mass matrix will always be a diagonal mass matrix when the body coordinate system is located at the center of mass. The moment we do it at the center of mass, mathematically you will realize that this term automatically becomes zero. So when these non-diagonal terms are zero, it will automatically become a diagonal mass matrix, right? So it is 83. We got 86, right? 89, and no one guessed 89 in the chat window, and no one even in the class guessed 89%. Okay. So for people who are not able to log in, maybe you can use some another web browser, and maybe that will help. Okay. So moving on, what I will do, I will already make the next quiz available to you. Okay, but I will explain that, and then you guys can answer it. So I think it would already be available to you in your Socrative. Don't answer it now. You can answer after a while. So moving on. Now let's talk about quadratic velocity vector. If you learnt earlier in this explanation that I was saying that when we try to express the inertia forces in terms of generalized coordinate, we end up with this huge mathematical expression. But when we try to simplify, we realize that this q inertia is a mass matrix multiplied by the acceleration of the generalized coordinate and a term which is quadratic velocity vector. Correct? So now what is this quadratic velocity vector? This quadratic velocity vector, when you take that term, you will realize that this term will have again three elements. Why three elements? It's because our generalized coordinate has three for a body in space. I'm talking about just one body in space. Okay. Okay. So for one body in space, we have three generalized coordinates, and when you try to express the inertial reference force, you will end up mass matrix multiplied by the acceleration of the generalized coordinate minus the quadratic velocity vector. So quadratic velocity vector will also have three elements, correct? And these out of these three elements, the third element, which is over here, will always be zero no matter what. And only two elements, which is corresponding to Rx and Ry, these two terms will be non-zero, but not always. So if you see this figure, when so this is the center of mass and this is a point which is the body coordinate system. Whenever your body coordinate system is not at the center of mass, your quadratic velocity vector will have these non-zero terms here, which is dependent on the angular velocity whole to the power square. So that's why we are saying quadratic velocity vector. And what is the physical interpretation of this quadratic velocity vector? The physical interpretation is that it accounts for the centrifugal force at that point where you are considering your body coordinate system due to the rotation of the body. So if I take a classical example, if I consider this pen and the center of mass is at the center, right? And you place your body coordinate system here and try to rotate, you will not feel the centrifugal force, correct? But the moment you have the body coordinate system at some other point, you will start feeling that there is some kind of a centrifugal force acting, which is resisting, which is hindering you to rotate this body, right or wrong? So that's why whenever the body coordinate system is at some other position other than the center of mass, you will have these terms there. But the moment you place your body coordinate system at the center of the mass, the quadratic velocity vector will become zero. So basically, this will become 0, 0, and 0. All the three terms will be 0, 0, and 0. So some people are already guessing it to be 100% the next in class quiz. So should we move on to the next in class quiz, guys? Yes, everyone is excited. So we have the next in class quiz. So I'm saying, when is the quadratic velocity vector 0? Is it when the body has a beam like shape? Not a big fan. Is it when the body reference coordinate system is located in the center of mass? Maybe, maybe not. Or is it when the body coordinate system is located out of the center of mass? I don't know. I have to do the maths. Or is it when the body coordinate system is located outside the body? So I think I'm going to take a picture and send it to Aki. So some online participants are saying 92%, 98. What are your guesses, guys? 99? So you are sure that at least there will be one student who will make it incorrect for the purpose that Aki don't dance. I'm sure Aki is reading these comments as well. But I'm very positive, guys. When I came to know that today I will be delivering this lecture, I was kind of prepared that today I want each one of you to answer it correctly and gain as much points as possible. So I'm expecting for each in-class quiz we will have 100%. But now it's completely up to you guys. So let's see how's the response for the in-class quiz. So 66. Should we wait for another couple of minutes? 69. I think last time it was around 65, right? Yeah, 71. We'll wait for another 30-second, guys. Please try to answer if you haven't. Yeah, a can-do attitude can make 100% success rate. You're right about that. What is CIR? Someone is saying that a can-do attitude can work, but then there is CIR. I don't know what is the full form of that. Uh, Guys, once you are logged into your Socrative, don't just delete that. Try to be there. So is this some joke from the earlier courses? Coffin, ibuprofen, and respect. At least I know you guys do something like this for respect, right? So respect if we have 100%. So should we see the answer already? Okay, we are ready. Moment of truth, guys. Should we? Oh my god. Guys, this was very close. 97%. How come, guys? How come? I already told you. So at least there are two students who doesn't want the success rate to be 100%. Is it amongst some of you or from online participants? Yeah, someone is definitely trolling us. Okay, we are getting close. We started with 89, 97, very soon 100. Okay, let's go on to our slides. Okay, so moving on. Now we have covered the leftover from lecture 5. Now you know what is quadratic velocity vector, and all the information that you have gathered so far, we will be using it. So someone is saying in the chat window that it is Aki who doesn't want it to be 100%. So he logged in and did an incorrect answer. Maybe. But anyways, so whatever you have learned so far, you have learned the expression of external forces in terms of generalized coordinate, the expression of inertia forces in terms of generalized coordinates, and we will be using these two information to formulate our equations of motion. But remember, guys, you also learned something about constraints during the earlier course, so specifically in lecture number 6 and lecture 2, right? So we will use all of this information to form the equation of motion. And if you have been following the tutorial, I already told you these are the detailed equations that you are learning now. But when you try to do with Simscape's multi-body software, in that the same equations are being solved for you and you don't know, you are kind of an end user there, but today you will have an experience about what are these detailed equations. So far we have been dealing with only one single body, right? And we tried to express the external forces and inertia forces for that single body. What we are going to do next is we are going to say that there is not just one body but a number of bodies together. How many bodies? Let's say there are nb number of bodies. Okay, and these nb, for these nb number of bodies, we try to accumulate or we try to gather the virtual work for the external forces as well as the virtual work for the inertia forces, right? This is that place where this concept of virtual work is kind of misused. How, I will explain you in some time. So what we can do is we can basically sum up all the external force, all the virtual work done by the external forces and the inertia forces, and the sum of it will express the total work, the total virtual work from the inertia forces. So basically this part, the total virtual work from the inertia forces and the total virtual work from the external forces, correct? Okay, we are making an assumption that assume that this work done and this work done are equal. Okay, the moment we make them equal, if you remember from the virtual work from the inertia forces, the expression is something like this. So this is delta. Okay, and basically we had, for the inertia force, we had mass multiplied by the acceleration of the generalized coordinate minus the quadratic velocity vector. Very good. So this is on the left hand side. And then on the right hand side, we have again the same virtual displacement multiplied by the external force vector. And external force vector is expressed in terms of generalized coordinate, right? Okay, so we are assuming that the virtual work done by this external force and the virtual work done by the inertial forces, they are equal. Okay, and as a result of which, when we make them equal, we arrive at a situation that m q double dot minus qv minus qe and whole thing multiplied by delta q, this will be equal to 0. Yes or no? So we are kind of following the same principle, that mass into acceleration is equal to 0. So basically, from Newton's second law, that any external force is equal to mass into acceleration, but they are expressed in the general in the global coordinate. We are just trying to express them in the generalized coordinate and then trying to take a virtual work of that particular thing over here. Okay, so remember this expression, it will come again. So when you see this expression, what is this m? This m is the mass matrix, this q is the generalized accelerations, this qv is the quadratic velocity vector, and this qe is the external force vector, and all of them are in the generalized coordinate, right? So now when we talk about the mass matrix, you remember the mass matrix earlier was something like, where is my mouse? Okay, it's here. So the mass matrix earlier was some m1, then 0 0, then there was some mass moment of inertia, let's say it's m1 l square by 12 for a beam, and then there will be some cross coupling term. It can be 0 if it's on the center of mass, the body coordinate system, right? But this is for one body, this is just for body number one, right? But we need to have this mass matrix for the entire system. How we can do? We can simply arrange them in this fashion, in a form of a diagonal mass matrix. This approach is very different from the approaches that some of you might be familiar from the finite element method. In finite element method, whenever we try to over there we deal with elements, and whenever we try to assemble the elements, we always assemble in such a way that there are some cross coupling terms between these elements, right? Like this, there are some cross coupling terms uh, between these elements. But in this one, all of the bodies are treated as independent bodies. So accordingly, you arrange your mass matrix in a form of a diagonal mass matrix like this. Correct? So this is how it is. The similar fashion will go for the quadratic velocity vector, that you will arrange it in a vector form where each element of this matrix is representing the quadratic velocity vector of an individual body. Is that right, guys? And similarly for the external force vector as well, you arrange that in a linear fashion. Simple as that. Okay, now comes the very important part, and the part is, first I would like to go over here again. So when we considered this equation, can you see already, or is it complicated? Okay, I will try to draw it here again. Okay. Okay, so this was the expression that we had. Now in order to form the equations of motion, either this term will be equal to 0 or this term will be equal to 0. Correct? When the product of two terms are 0, then either one of them will be equal to 0. But in our case it cannot be true. Why? Because we know that this term cannot be equal to 0. This is infinitesimally small, the virtual displacement related to the generalized coordinates, right? So this term can be equal to 0, but can we really put that to be equal to 0? Yes or no? When we talk about bodies randomly in space, not connected to each other, in that case, definitely we can put this expression to be equal to 0. But in multi-body dynamics, you know that bodies are connected. They are connected using constraint equations, which we also called as joint. So, for example, this body and this body, when they are expressed like this, where there is no connection, then you can put this expression to be equal to 0. But the moment you say there is a connection between them, they cannot be equal to 0, because over here you are leveraging the use that, okay, bodies are independently expressed, but they are not independent, they are connected using constraint equation. So you need to incorporate this condition, which is called constraint equation, in this particular expression, and then forcefully we can make them equal to 0. Is that clear? Yes or no? Okay. So these constraint equations, we say that there are a number of I'm losing my mouse. So okay. So there are a number of NC constraint equations, and constraint equation is basically a vector that is arranged in a fashion as shown here, where each row is representing one constraint equation associated to your multi-body system. Okay, so this part I have already explained that in finite element method, your elements are cross coupled with each other, so there are cross coupling terms. But in multi-body dynamics, when you express the mass matrix, the quadratic velocity vector, the external force vector, there are no uh, cross coupling terms there, so they are all treated as independent bodies. But then we introduce this constraint equation to say that, hey, these bodies are not independent anymore. Okay, so what I explained you already, I'm trying to explain it again. So generalized coordinates are not coupled, right? So for example, if we have these two bodies, body 1 and body 2, we say body 1 has three generalized coordinate because every body needs three generalized coordinate. So Rx, Ry, and the angle of this body, correct? Similarly can be said about the second body as well, correct? And these generalized coordinates are not coupled, they are kind of independent, correct? So whenever we talk about the total generalized coordinate, the total generalized coordinate in the system are always the independent generalized coordinates, which is helping us to form the equation of motion, meaning forming the dynamics of the entire system, right? And how we can establish the dynamics? We can establish the dynamics from the concept of virtual work. What does the concept of virtual work says? That the work done by the external force is equal to the work done by the inertial force, correct? And exactly we have done this over here. We know that the work done is virtual displacement multiplied by the force vector, and now we are dealing in generalized coordinate, because you see these terms here, they are not the ones expressed in global coordinates but the ones expressed in generalized coordinates. Okay, so when we just expand these terms, we arrived at this situation which I already explained it to you, right? Okay, so for constrained multi-body system, whenever we have constraint equations, because when these bodies are connected with each other, then you cannot, by no means you can express this to be equal to 0. It cannot be equal to 0. Just keep that in mind. It cannot be equal to 0. Why? Because the constraints are not incorporated. Why? Because the constraints are not incorporated. Okay, but this equation, we can forcefully make it equal to 0 by using two approaches. These approaches are called augmented formulation and coordinate partitioning. What it means is we need to find a virtual displacement which is kinematically admissible, meaning that the the displacement for these two bodies, let's say the displacement for these two bodies will be such that it will not be against the kinematics of the body. It will not cause a displacement something like this goes here, and the linkage is broken. No, whenever we define this small finite this virtual displacement, it will be such that it will be kinematically admissible, and then only we can make it equal to 0. How that can be kinematically admissible? When we incorporate the constraint equations. And constraint equations can be incorporated in two ways: augmented formulation and coordinate partitioning. So I think it's the time for the next in-class quiz, that this equation cannot be set equal to 0 because inertia forces are not accounted, externally applied forces are not accounted, constraints are not accounted, or no forces are accounted. What do you guys think about this? Why this equation over here, it cannot be equal to 0? Why? For a constrained multibody system. And the game is on, guys. Please make your guesses. How much? For the in-class quiz, for the in-class students, if someone, so I have a little surprise for you. So I got some chocolates. Okay. So if someone is able to make the right guess, this chocolate will be yours. And I'm very sorry about the online participants. So once we are over with this quiz, then you make need to make guesses, and this chocolate will be yours. It will be rotten if I try to post this for online participants. So let's see. 66 students already answered it. 67. I think there should be four more, three more. So make your guesses, guys. What do you think? 95. Then 87, 88. Then 72. Please remember your numbers because I cannot remember numbers for all of you. 98. Okay. What about online participants? 96. Someone said. Okay. 93. Okay. I think everyone needs the chocolate. I am saying 89. Okay. I think no one selected 89. 100%. Still, someone is saying 100%. So I think everyone answered. Should we have a look at the answer? So you are saying 100. So it was 88, 98, 97, 90. So there was 72, 91. You say all the numbers. Someone will get it. Come on. Okay, 95. Okay, moment of truth. And I'm saying 89. Guys, who is that two people who are trolling us with not 100%? You and Aki. So it's Mostaba and Aki, guys. So who was? So I heard 97. Someone saying 97. No, you said 97. 98. You said 97. Yeah. 87. No one said 97. 97. We still have some in-class quizzes and two chocolates. So I'll save it for the next one. And I see someone in the chat window made 97% guess. And that was a right guess, but unfortunately, I cannot post it to you. But you deserve a chocolate. Buy one and have a chocolate on my behalf. Okay, so moving on, guys. Okay, so moving on. Now move on. We move on to the augmented Lagrangian formulation. So, like I told you, that we can handle constraint in two ways. One is the augmented Lagrangian that you will be learning today, and another one is coordinate partitioning that you will be learning probably after your midterm exam. And by the way, before I forget this, Next week, there will be a lecture from Professor Akimikola, and he will be basically summarizing everything that he has taught you so far. And he will also explain you what are the important topics that you should focus for the midterm exam. So, if you are planning not to participate, it's a wrong decision. I will suggest you to participate to that because he would literally tell you which topics to focus in order to get good points from the midterm. And the week after that, we will have midterm exam. So the midterm exam will be in week 43. I guess that is week 43. So 2 weeks from now. The midterm exam will be available for one entire week. It will be completely on Moodle. So under topic 1, you might be already seeing midterm exam 1, right? That link will be activated in 2 weeks from now, and it will be available from Monday till Sunday midnight, like your homeworks. And you will have two attempts. Okay, two attempts. My first suggestion to you would be make an attempt already during the start of the week around Monday or Tuesday. If you are scoring less point, study the lecture material, go through these lectures again, and then towards the end of the week around Saturday or Sunday you can make another attempt. And the best grades from these two attempts will be taken. So we will not average the score. We will take the best score, whatever you have achieved between these two attempts. Is that clear to all of you? Any questions regarding midterm exam? Good question. So you don't need to register for the midterm exam at all. It's online, it's on Moodle. So if you have access to Moodle, you can simply go there and take your exam. It's as simple as that. Perfect. So any questions from the online participants or anyone from over here? No? Do you guys need a short break? A 2 minute break, or you guys don't want to do that? Yes, no? Or should we continue? We were already late, guys. So I would suggest let's continue. Okay, so before we, okay, no need, perfect, no break. So before we have a look at the augmented Lagrangian, let's let's go to the basics. Let's go to something that you might have learned in your high school or during your bachelor's or maybe before that. Whenever we have an equation like this, we need to minimize this equation by accounting this condition. Okay, so you have an equation which is of second order, and you need to minimize this equation fulfilling this constraint. So what are these points, or what are these positions where this equation will have its minimum value within this limit, within this limit? How we can do that? So we can take this equation. These equation are dependent on two terms, y1 and y2. So what we can do is, first we can try to solve for y1. How we can do that? We can compute y2 from this condition and put it back to this equation, right? Once we do that, we have a form something like this. Then in order to find a maxima or a minima, what we do, we differentiate that equation. So what I am trying to do, we are trying to differentiate this function with respect to y1. So we are doing partial derivative of this function with respect to y1, and what we are obtaining this expression, which is 2y1 minus 1 is equal to 0. So whenever there's a maxima or a minima, the derivative will always be 0. In our case, we are trying to find the minimum, the minima. And minima can be obtained at y1 equals to 1 by 2. How we know this is a minima and not a maxima? When you try to double differentiate this using the same procedure, you will find an expression which is greater than 0. When it's greater than 0, meaning it's a minima. And I think this thing most of you have learned already. So there's no rocket science, I believe. Yes or no? A thumbs up or a thumbs down, guys? Everyone? Not so confident thumbs up? Okay. So moving on. Now we try to do the opposite. We try to compute for y2. How we can do that is we simply take the expression of y1 from this condition and put it back here, and following the same differentiation rule we find that this partial differentiation of this function with respect to y2 will be 0, and you know that if you double differentiate it, the value that you will get will be again greater than 0. So whatever, at whatever value this function is 0 is the minima, and what is that value is y2 is equal to minus 1 by 2. So now you have two conditions. So basically this equation will have a minimum value when y1 is equal to half and y2 is equal to minus half, correct? And these values are also fulfilling this condition. So we were able to find the solution within this condition. Now moving on, a more generic expression of what we just learned from Wikipedia, and how this might be important for us for the equations of motion, because so far I have been telling you forces, external forces, inertia forces, generalized coordinate, and then all of a sudden I'm asking you to minimize a function with respect to a condition, right? It is important for us, guys. I will explain you, but before that, so you can find an extreme of a function which is subjected to a condition or a constraint, in this case this equal to 0, in such a way that the extreme value can be found that when this function gx and these function fx, when the gradient of these functions are parallel to each other. So this gradient in this direction and this gradient in this direction, they will be parallel and equal to each other. Exactly at that point, you will be, so exactly at this location, you are fulfilling the constraint or the condition that was imposed to you, and at the same time, you are able to find the extreme of the function that was under concern, right? So if I go to this case, this was my fx, and I was trying to find the minima of this one using this constraint equation gx, just a generic condition, right? So now moving on, so more detailed explanation about this is, as I told you, their gradients should be equal. And how do we express gradient of these two functions? We express the gradient using this reverse delta. So saying the gradient of this one should be equal to the gradient of the function g. But it's not necessary that the gradient will be the exact equal, will be exactly equal to the gradient of the function, right? There you have to multiply it with some scalar quantity in order to have that equal sign. So how you can multiply? You can multiply it with a Lagrange multiplier, with a term which is called Lagrange multiplier. This term will ensure that the gradient of your function under consideration is equal to the gradient of the condition multiplied by the Lagrange multiplier. Now, if this explanation is difficult for you, don't worry. I'm trying to explain this from the point of multi-body system dynamics. This is no rocket science or no like huge mathematics involved in it, but something that you have learned already, and now we will try to connect dots from your past to your present. How? So suppose we have a function. Where is my cursor? So we have a function which we want to minimize using this constraint. The same example what we saw earlier, correct? And over there we kind of we were solving it using partial derivatives and then putting that equal to 0 and then coming up with the value of the variables to find that condition, right? Over here we will try to do a similar thing but with the augmented lagrangian fashion that I just explained you. So what you can do, what primary variables do you have here? You have y1 and y2, right? So these are your primary variables, or you can also say generalized coordinates, correct? So now try to take the gradient of this function q and this function g with respect to this primary variable with respect to this generalized coordinate. So when you take the gradient, what is gradient? Gradient is just partial derivative operation. So you are trying to make the partial derivative of this function q first with respect to y1, then with respect to y2, and the gradient will be a vector which is y1 and y2 if you just simply uh, make the partial derivative of these with respect to y1 and y2. Is it confusing? Simple? Okay. Similarly, you do the same for this function g. How you can do that is basically partially derivating it with respect to y1 and y2, and you get this vector. Now, what I explained you about the augmented formulation approach is this gradient will be equal to this when it is multiplied with Lagrange multipliers. And exactly we will do that. What we do is we come up with this conditioning. In this case, we are multiplying it with minus lambda, and this equation needs to be considered along with the condition as well, because this equation alone cannot determine everything, because you are introducing another variable which is lambda, and you don't know what is the value of lambda. So from this condition these two equations are coming. You already have an unknown y1, you already have an unknown y2, and then you incorporated another unknown which is lambda. But so there are three variables and only two equations here. So you need another equation, and what is that equation? That equation is your condition itself. So that equation is your constraint equation itself. And so once you incorporate this constraint equation itself, you can have three equations, three unknowns. And when you solve them, you get the same value as of y1 and y2 as 1 by 2 and minus 1 by 2. This is something we just did a while ago, correct? Yes or no? A thumbs up or a thumbs down? You guys seem sleepy. So the next in-class quiz is coming. Okay. Everything is clear for online participant as well. Perfect. So this is one story I was telling in my tutorial session, that whenever I see sleepy faces, I kind of miss my student days when there was used to be fat boys in the library. So if you go on the top floor of the library where there is this corner where there is an exercise, you can do some exercises carry out. So that used to be a sleeping place with like huge fat boys there. You can simply go and sleep there, and I have done that multiple times. And trust me, from my experience, sleeping in the library is a different fun altogether. So whenever I see you guys sleeping in the classroom, I feel like you should go to the library, take your own fat boys and sleep there. But anyways, moving on. So a more generic expression about what we just learned is when we have a function, again I lost, okay. So when we have a function f and a constraint equation g, then we can find the minimum of this function fulfilling this constraint when this condition is being fulfilled, saying that the gradient of the function is equal to the gradient of the condition multiplied with Lagrange multipliers. And this alone is not sufficient to solve everything. You need the condition itself to solve everything. Now you see, you're trying to see the relation between what I just explained and what we have been following from the multibody point of view. When I said you that this equation mq double dot minus qv minus qe whole thing multiplied by delta q is equal to 0, and in that case we wanted to put this equal to 0, but we could not. Why? Because the conditions were not fulfilled, the constraints were not fulfilling. So now, about what I explained you just now with what we have. In our case, this gradient is basically this term here, and the gradient of the condition is basically the Jacobian of the constraint equations with respect to the generalized coordinate. Yes or no? So how we can arrive at this mathematical expression is that when we incorporate the gradient of the condition, so the gradient of the constraint equations. Once we do that, then then this entire expression which was equal to 0, it should be, the actual form should be this, where we have incorporated this Jacobian of the constraints. Now this expression inside this parenthesis can be equal to 0. Why? Because now bodies are connected using these condition. What is that condition? Constraint equations. Yes or no? A thumbs up or a thumbs down? Everyone? Online participants? Okay, no comments. I am assuming it's okay for you as well. Okay, thumbs up. Very good. So now, as I told you, this equation alone cannot solve everything. You need the condition itself as well, right? So this equation alone cannot solve everything. Why? Because there are some additional variables as well, and you need to incorporate the condition, that is the constraint equation as well. Now, so far, if you are with me, well and good. We have almost reached to our forming the equation of motion from using the augmented Lagrangian formulation. Now, if you see this set of equation, the first set of equation is differential equations, and the second set of expression is algebraic equation. So this form is called differential algebraic equation, DAE. But and also there are some numerical integrators that can solve such differential algebraic equations, but my suggestion to you, and it's a very common practice in multibody dynamics, that we try to convert this entire differential algebraic equation into ordinary differential equations. And then there are many different integrators which are available to solve ordinary differential equations. For example, connecting it with your tutorials, OD45s. Whenever you go to the solver setting, you have OD45, OD15s, OD23. So these are the different integrators. Now you see, now you're trying to make the relation. Okay, so we need to convert this differential algebraic equation into ordinary differential equation. How we can do that? So this conversion can be done by double differentiating the constraints. When we double differentiate the constraints, we see something similar with respect to kinematic analysis. When you guys were doing kinematic analysis, you were dealing more or less with a similar term at the acceleration level. Yes or no? So if you see this term will be exact similar from your kinematic analysis. So meaning that when we are double differentiating, we are trying to say that the acceleration level constraints are also being fulfilled. And instead of this C, we consider this expression because this is also differential equations. And when we consider this equation and this particular equation, we can form this sophisticated expression, which is your equation of motion using augmented Lagrangian method. So if you see the first half of this equation, this is exactly the same thing as in here. And when you see the second half of it is exactly this part. Is there any confusion, guys? Yes, no? And what is the physical interpretation? So guys, I think the in-class quiz is coming. What is the physical interpretation of this Lagrange multipliers? The physical interpretation of this Lagrange multipliers that it is representing reaction forces. If I talk about a simple pendulum, how many generalized coordinate does a simple pendulum need? Everybody needs 3 generalized coordinate, right? And when I am constraining this over here, so this is constrained using a revolute joint in 2 dimension. How many constraint equations does it need? 2. The number of variables that you need for Lagrange multiplier will be equal to the number of constraint equations that you need. So in this case, there will be 2 reaction forces at this point, in the x direction and in the y direction, right? So for a simple pendulum, the number of generalized coordinate is 3. The number of parameters Lagrange multipliers is 2. So there are a total of 5 variables that you need to solve in order to arrive at this, in order to solve this equation of motion. Is that clear or no? Okay, we are running out of time, so I will quickly summarize what we have done so far. So repeating it again, we could make this virtual work to be equal to 0 when we incorporated this Jacobian of the constraint equations incorporating Lagrange multiplier. So when we make it equal to 0, then we had this term in the bracket was equal to 0, and also we were considering the constraint equations along with it. But we realized this is expressed in the differential algebraic form, and this differential algebraic form needs to be converted into ordinary differential equations because ordinary differential equations are simple to solve. And how we can do that is when we double differentiated with this constraint equations, we come up with an expression like this, which is kind of a kinematic analysis at the acceleration level. And then instead of this C, we are incorporating this term, and then we form the ordinary differential equation. The detail of this, if you want to read, it's available in the lecture note. But I think the concept might be clear to you, right? Okay. So coming with the first, so the first in-class quiz for this augmented Lagrangian, and with this we can close the lecture. But the question is, in the augmented formulation, how many unknowns are there? Are the unknowns only the acceleration of generalized coordinates? Or is it just the Lagrange multipliers? Or is it the generalized forces? Or is it a combination of acceleration of generalized coordinates and Lagrange multipliers? So if you see this equation, it's asking how many unknowns or how many variables you need to solve. So I just explained you with the example of a simple pendulum, and if you try to follow that explanation, try to imagine how many variables you need to solve using augmented Lagrangian formulation, and then try to answer it. And the game is on for the chocolate. Our online participants with me, 98. I am so I am guessing it to be 100%, provided Aki and Mostaba are not trolling us. Mostaba, is Socrates on? So okay, guesses guys. 97, 87, 95. There are 295, 297, so we have two chocolates. 98. I'm saying 100%. Online participants are saying 89, 98, 97. So more or less the same number. So someone is saying there are two people who are trolling us, so it will be 97. So we are waiting for more four participants. Okay, one more and then we are good to go. Okay, so the moment of truth, guys. Can you say your numbers again? 97, 95, 81. Who is 81? 92, 90. Please remember your number and be honest, okay? Be honest, guys. Okay, so the moment of truth. Are we ready, guys? Should we see some dancing from Aki? Are we able to do it today? Ooh, it's not 100%. I lost. So who said 92? This chocolate is yours. Can I throw it? Okay, you can come. So there is one winner in the lecture. A clap for him. Welcome. So someone guessed it right, 92, and he gets a chocolate from me. This was your last chance to get a chocolate because I won't be coming next week. So maybe next time you can ask Aki for the chocolates, okay? But anyways, guys, so let me explain you this one more time and then we'll go. And there was no 92, 92, right? There was no 92 for the online participants, so nobody won from the online participants. So in augmented formulation, the unknowns are generalized coordinate and Lagrange multipliers. So the unknowns are generalized coordinate and these Lagrange multipliers. So this is the vector of unknown. This is the vector of primary variables in Lagrange augmented in augmented Lagrangian formulation. Is that clear? Yes? Okay, if so, then we will close this lecture because it's already time and we started with a delay. But then there were a couple of slides after this, which is mainly the examples about how to formulate these equations of motion for different examples. Maybe Aki can cover this in the next lecture and then we can proceed with the summary. So thank you so much, guys. You guys have been a great audience. Have a nice evening and thank you for the online participants as well. Thank you, guys. I will stop the streaming.